Hello and welcome to a lecture on transistor fundamentals. I'm Steve Ellingson. Here's an overview of this lecture. We're going to be talking about transistors as they apply to RF engineering. There are two major classes, the bipolar junction transistor, or BJT, and the FET. For the BJT, we'll talk about terminology, some conventions, the method of operation in terms of their use as RF amplifiers, some terminology, the different kinds of bipolar junction transistors that are out there, and their use as common emitter amplifiers. This is just one of several configurations. It's the most common one for amplifiers, but there's certainly others, and we'll talk about those. We'll also talk about field effect transistors, or FETs, or FETs. Again, terminology and conventions, method of operation, technology, that is the variants that exist out there, and the most common configuration for amplifiers, which is the common source amplifier. Although again, there are different configurations, so we'll say a little bit about what choices we have beyond common emitter for BJTs and common source for FETs. Here is the bipolar junction transistor. This is a schematic element that I'm sure you've seen before. We indicate the transistor using this symbol. The arrow pointing in this direction outward indicates that this is an NPN, referring to the arrangement of the semiconductor materials within the structure. Also has some effect on the way it behaves. There are also PNP BJTs. Everything is pretty much the same with just a few very minor changes. So we're going to talk about NPNs here. The differences with PNPs is very, very minor. The three terminals of the BJT are the collector, the emitter, and the base, indicated with the symbols C, B, and E respectively. At the collector we have a voltage, V sub C, and a current, I sub C. I sub C is defined to be into the transistor by convention. At the base we have V sub B and the current I sub B, with the current again flowing into the transistor. And at the emitter we have the voltage V sub E and the current I sub E, but in this case I sub E flows out of the transistor. Here's one of the governing relationships for a BJT. The collector current, the current flowing into the collector, is given by a constant, I sub C naught, times E raised to an exponent equal to V sub BE. That's the base emitter voltage. That's the difference between these two terminals, divided by V sub T, which is the thermal voltage. The thermal voltage is given by K, that's Boltzmann's constant, which is 1.38 times 10 to the minus 23rd joules per Kelvin, times T, that's the physical temperature of the device, divided by Q, which is the charge of an electron. That gives you 25 millivolts at room temperature, plus or minus a small amount. But this gives you an idea about how the collector current varies with the base emitter voltage. The way we use BJTs as amplifiers in RF designs is to bias them into the forward active mode. This is the mode in which the transistor behaves like an amplifier. And here's a diagram of the equivalent circuit of a BJT when it's in the forward active mode. What we see is that the base current flows into the emitter. The diode there prevents it from going back in the other direction. And then the collector current is constrained to be equal to beta, this constant, beta, times I sub B, times the base current. So we see that the collector current depends on the base current through this constant beta. Now, to be in this mode where this works in this fashion, V sub CE, that's the collector emitter voltage. The voltage between the collector and emitter pins has to be greater than about 0.3 volts. That puts it in the forward active region. In this state, then V sub BE, the base emitter voltage, is typically about 0.65 volts plus or minus half a volt. Again, different for different transistors and different operating states, but not by much. The DC current gain is beta. That's the constant I used there. Beta from this diagram then is I sub C divided by I sub B. And there's the ratio of the collector current to the base current. And that ratio is typically somewhere between tens and hundreds. This value beta is determined by the bias, also known as the operating point, also sometimes referred to as the Q point. All these terms mean pretty much the same thing. The specific value of beta is highly variable, even between identical model numbers. So you can have transistors coming off an assembly line and the values of beta will vary significantly. So one of the difficulties or important things to do in an RF amplifier design is to make sure that the design is insensitive to the precise value of beta. So more on that in a future lecture. An important note here is that the BJT works like a current-controlled current source, right? In other words, as indicated here in the forward active mode, the collector current depends on the base current through this value beta. So as we change the base current, the collector current changes, and this is how we get amplification in the RF amplifier application. It's useful to know something about BJT frequency response. You may know or not know that the realizable gain of a BJT decreases with increasing frequency. Now we know already that there are many ways to define gain, but it really doesn't matter which definition you use. In all cases, that gain decreases with increasing frequency. The main reason for this is due to internal capacitance inside that transistor. That typically accounts for about a 6 dB per octave decrease. So all the various types of defining gain tend to decrease at about the same rate as shown in this plot, which is for a typical relatively high performance, though, BJT transistor for RF applications. It is common to define a unity gain bandwidth given by the symbol F sub t. This is the frequency at which the change in collector current relative to the change in base current, these are the relevant RF values, is equal to 1. In other words, has decreased until it's 1. So we can show that quantity here. It's indicated as gain, so it's taken as magnitude squared of this relationship. For this transistor, this condition occurs here at about 5 gigahertz. So we would say 5 gigahertz is the F sub t, or the unity gain bandwidth. This is not normally a place where you would operate the transistor. It's simply a single number which gives you something about how high a frequency at which this transistor could operate. For this particular transistor, it's far more likely that we would use it in this regime where the gain is appreciable. Okay, now something about BJT technology families. Well, you probably know about good old silicon transistors. And in RF applications, these typically give us F sub t's in the range of 100 megahertz up to about 4 gigahertz or so. Now remember, this is F sub t, so the usable range of frequencies, at least if you need any appreciable gain, is typically much smaller than this. So maybe something like 20 megahertz for 100 megahertz F sub t, and 1 gigahertz or 500 megahertz for 4 gigahertz F sub t. We also have heterojunction bipolar transistors, also known as HBTs. They have somewhat higher F sub t's. They go up to about 100 gigahertz or so. So they have usable gain up to about 10 gigahertz or so, depending on the particular transistor. There are many ways to make these. They include semiconductor materials such as gallium arsenide, silicon germanium, indium phosphide, INGAP, as it is sometimes referred to, and increasingly complicated combinations of materials that allow for improved performance and higher F sub t. And also, BJTs can increasingly be integrated into CMOS. So, for example, BiCMOS is a BJT type technology. It's a way to implement BJT transistors on the same kind of silicon material that you'd use for digital logic. And that pays dividends when you're trying to make very, very small devices. There are basically two aspects to design. We've already seen this in previous lectures. One, of course, is going to be biasing. That's going to be setting the quiescent values of V sub CE and I sub C. So typically taken together, those two values define the bias point. We set V sub CE to be greater than 0.3 volts or so to ensure forward active operation, and then we set I sub C in such a way to achieve other design goals that we're looking for. The term quiescent here refers to what these values are when there is no RF signal available. So we bias it to some value, and then of course the RF signals will be very, very small deflections relative to that value. The second aspect to design is small signal, or what we might say here specifically RF design. And typically that's achieved by designing input matching networks and output matching networks to achieve gain, Viswar, noise figure that's specified. So these are the two aspects to design: biasing and small signal design. Now, let's connect this back to S parameters, which we addressed much earlier in the course. Typically, we need S parameters for the small signal design, and those values depend on frequency, obviously, we already know this. They depend on the bias, and you will recall that values of S parameters we've used in the past were read from a table. At the top of that table, it would say what value of V sub CE and what value of I sub C those S parameters applied to. And if you change that bias, then the S parameters themselves change. And then, of course, the S parameters also depend on how you're using the transistor. In other words, is it common emitter, common collector, and so on. And the reason that is because, well, here's the common emitter configuration. That would be the input. That would be the output. So it depends on how the transistor is oriented. If you change the orientation of the transistor, in other words, use another terminal for input and output, then the S parameters also change. Also, the circuitry that determines bias and the circuitry that determines small signal performance must be combined. So this is something that we're going to find is one of the challenges in RF amplifier design is how do you design circuitry that sets the bias where you want it, but also allows you to set the input and output impedances and can be combined. So these two things, the things that set the bias and the things that set the input and output impedance, can coexist. In particular, one thing that turns out to be a challenge is how to keep the RF and DC separate. For example, you don't want RF running into the power supply and bypassing the signal path, and you don't want DC necessarily traveling from component to component in the signal path. So this turns out to be a large part of the job of designing transistor amplifiers. Let's talk about the common emitter configuration in a little bit more detail, since this is the one we see most often, but again, not exclusively. Here is the orientation for common emitter. Input is taken and applied to the base. Output is taken from the collector. We have to bias the transistor somehow. And then also, I'm showing here blocking capacitors, or as we say, blocking caps. And the purpose of those blocking capacitors, as shown in this diagram, is to keep the DC from flowing out the output or out the input. Now, these may or may not be actual capacitors here, and there are other ways to block the DC, but frequently you will see something like this, and they will be there for that purpose. In the common emitter configuration, BJTs have relatively high current gain. They have relatively high output impedance, which is useful for isolation from subsequent stages. That reduces the tendency of subsequent stages to interact. And these, of course, are things that are often desirable in an amplifier. These concepts should not be completely new to you. They're standard ideas for a wide range of applications, including relatively low frequency design.